Hi everyone, in this lesson we're looking at solving real-world problems, and we're going to be using our calculator for some of these, looking at the graphs, and then we'll be doing some of these analytically. So prior knowledge content, real-world applications with and without technology. And on this page is just really a review of the formulas, and these should all look relatively familiar to you. We have growth and decay formulas here. We have a compound interest formula. Most of these you do sort of already have to have memorized, but there are some that are in the formula booklet. So let's look at the formula booklet. If you look at topic 1, you'll see that the formula for the compound interest is here. All right, now it's written not such a nice way. I prefer the way I have it written, but we have FV. FV is future value. So what your output is going to be. PV represents your initial value, your present value. They're just saying that if they give it to you in a percent, then you have to convert it to a decimal by dividing by 100. So it's the same thing that I have, in your notes, just written slightly differently. And K is the number of compounding periods per year. So same formula, just written a little bit differently. And as far as other formulas you might need on this page, you can use logarithms to solve some of these problems, so that will come up as well. We have distance, rate, time problems. I'm sure you're very familiar with distance equals rate times time. We might need it by solving for t or by solving for r, but the main formula, of course, is distance equals rate times time. We're going to solve an equation by finding the intersection on the calculator. These are the steps that you would need. I will show you in the video. And maximize and minimize values. All right, that is when we're going to be looking at either a maximum or a minimum of a graph to find those types of values. All right, so these are the formulas overall, and you're just going to have to read the problem and then decide what do you need to use. All right, number 1, the population of turtles in an isolated colony is given by this formula, where t is the time in years after the colony was first recorded. How long will it take for the population to reach 1,000 turtles? So what we're saying here is, when is that formula going to reach 1,000? So let's write that out. What is the time value for that? So you could solve that algebraically using a log, or you could use your calculator. I'm going to do it with my calculator. So the first thing we're going to do is we're going to enter this into y1 and this into y2. Do that first. And then we'll look at the intersection of those two graphs. So we're going to go to y equals, and we're going to enter in the left side of the equation and the right side of the equation, and we're going to look at the graph. Now, if you look at the graph in a standard window, so let's say we did zoom 6, you're not going to be able to see it. If you want to fit the window to your graph, a really easy way to do it is you're going to go to zoom 0. You're going to go to zoom fit. All right, we're going to go to zoom fit, hit enter. All right, perfect. Now we can see the graph. And now what we want to do is find the intersection, and then we'll know the value. We'll find our solution. So we're going to do second trace, and we're going to pick number 5. And it automatically will put your little spider on the first curve. So all we have to do is hit enter. Then it will automatically jump the spider to the second curve. We hit enter. And when it says guess, we hit enter again. All right, so our value here is 2.3673064, which is rounded to about 2.37. And you always want to, when you're doing real world problems, is kind of examine your answer and make sure it makes sense for the problem. So the initial population of the turtles was 852. Right? Now we're saying, well, how long did it take for the turtles to get to 1,000? Makes sense that it would be around 2.37 years, about 2 years. That sort of fits in with this problem. All right, same idea for part B. We're going to set 1,500 equal to our equation. And we're going to solve for t. You could use a log if you want. If you enjoy using logs, feel free to do that. Should get the same answer. We're going to enter 1,500 now instead into the y value in our calculator. Same graph should work. We'll hit graph. If it didn't work, you could do zoom fit again. We're going to do second trace. Number 5 for intersect. We hit enter, we hit enter, we hit enter. And we get 8.36. All right, that is it for number 1. Casey invested $1,225 in a certain bond that pays 19% interest compounded annually. How long will it take for Casey's investment to triple? So right off the bat, we know we're going to need a compound interest formula. All right, so we're going to write out the formula first. I always find that helps. And now we'll fill in the formula based on the information for the problem. So they want to know how long will it take for Casey's investment to triple? So the output amount is going to triple. So 3 times the original value, I'm going to get 36.75. Okay, so for the output value to be 36.75, my initial value is 1,225. My rate is 19%, or 19 divided by 100. That's going to give us 0.19. My value of n in this case is 1 because it says compounded annually. That's going to be 1 time per year. And then t is the value we're looking for. And it might be helpful to underline, like, how long will it take? That means that you're looking for a time value. All right, and so we're going to do the same thing. We're going to solve this for t, but I think for fun this time, I'm going to use a log to solve it just to demonstrate that. So first of all, let me just clean this up a little bit. And we like logs because logs allow us to, if we have a variable as an exponent, we can bring it down if we use a log. So before I take the log of both sides, I also just want to clean up. I want to divide both sides by 1,225. Now at this point I could take the log of both sides, and I'm going to take the log of 1.19 of both sides, because log base 1.19 of 1.19 is just 1. So let's write that out. So we'll take the log of 1.19 of 3. Take the log of 1.19, so I'm taking the log of 1.19 of both sides. Now, that's what I was saying right here. This is equal to 1. Log base 1.19 of 1.19 is just 1, just like log base 10 of 10 is 1, or log base 3 of 3 is 1. All right, so what are we left with? And we're just going to put that in our calculator. I'm going to go to math. You're going to scroll down to log. We're going to enter log base 1.19 of 3. We're going to get approximately 6.32 years. Okay, moving on to number 3. A material of 490 grams decays at a rate of 0.94% per year. How much material will be left after 9 years? So we know we're talking about a rate of decay problem. We're going to write that formula out first. Okay? We want to know what material is going to be left after 9 years. So we're looking for the output value this time. We're trying to find y. The initial value is 490. Our rate is 0.94%. Well, you have to divide 0.94 by 100 or move that decimal 2 places to the left because we want it in decimal form. So minus 0.0094. And how much material will be left after 9 years? So that time value is going to be 9. And then we'll just put that into our calculator and solve it. And we're going to get 450.07. And IB really likes you to include those units. I have to admit, I forget a lot about doing that. I think they will take off like a small percentage of a point if you don't write, for example, on this problem, grams when you circle your final solution. Number 4, the population of Somerville, New Jersey in 2011 was 12,143 with an annual growth rate of 0.24%. What is the population estimate for Somerville in 2020? So this is a growth problem. So we're going to write the growth formula first. We're looking to find the output value. We want to know how many people are going to be in Somerville in 2020. So we're looking for, again, our output value. Our input is the initial amount of people. Our rate is going to be 0.24 divided by 100, or move the decimal 2 places to the left. And the initial amount was in 2011. We're talking about 2020, so that's 9 years later. So we put 9 in. We'll put that in our calculator, see what we get. We get 12,000. We're not going to do a point of people. We'll round to the nearest whole number. We're going to do 12,408 people approximately. Okay, moving on to number 5. We have Matt put $9,870 in a 3-year CD that pays 9% compounded semi-annually. Semi-annually means twice per year. All right, we're talking about compound interest here. What is the amount that will be in the bank after 3 years? So we want to know the output value. We want to know the final amount. So let's write the formula as always. We're looking for the output amount, so we're going to be looking for that A value. Our initial value is 9,870. Okay, our rate, it says 9%. So divide 9 by 100, or you could think of it as moving the decimal 2 places to the left. N value is how often per year we're compounding interest, so that's twice, so that's 2. So N is 2, and our time value is 3 over 3 years. And we just put that in our calculator and solve. We're going to get 12,853.31 approximately. Okay, problem number 6. For what positive number is the sum of the number and its reciprocal minimized? So as soon as we see minimized, we know that we are going to be looking at the minimum value on the graph. All right, so let's read that again. For what positive number is the sum of the number, I'm going to call the number x, and its reciprocal would be 1 over x. We're looking at the sum. So our equation is y equals x plus 1 over x. And we want to find the minimum value on that graph. So let's put that in our calculator. All right, so we have that entered. We're going to do a zoom 6 for a standard window so we can see the graph. We want to find the minimum value in this graph, right? So we're going to go to second calc. We're going to pick number 3. Again, the directions are on your notes on the first page. All right, we're going to move our little spider to just a little bit to the left of that minimum. We're going to move our little spider to the right and hit enter. When it says guess, we just hit enter, and we get our minimum value at approximately, right here, at approximately 1. I'm going to do a quick sketch of the graph. So in this case, our answer is x is approximately 1. Okay, the next one says the sum of a number and its reciprocal is 29 over 10. Find the numbers. Okay, so we basically have the same equation that we had in number 6, the sum of a number and its reciprocal. And that's going to be equal to 29 over 10. Find the number. Okay. So we want to either solve this algebraically or use our calculator to do it, right? I'm going to use my calculator. So we already have the left side of the equation there. Now we're going to enter 29 over 10. And we're going to look at the graph. So we're looking at the graph and we're seeing that we are intersecting in 2 places. So we know we have 2 solutions. And so we just need to find both of those intersection points. So we're going to go to second trace again for calc. And we're going to find the intersection. And we're going to move our little spider near the first intersection and hit enter 3 times. So our first value of x is going to be 0.4. Then we'll go back to our graph. We're going to do second calc, intersect. Move that little spider near that intersection, just right near it, and hit enter 3 times. And this time we get 2.5. So our solution for this problem is 0.4 or 2.5. Now, if you really like algebra and you want to solve this algebraically, feel free to do that. You should still get a solution of 0.4 and 2.5. Moving on to number 8. There are 2 positive numbers. The second number is 1 larger than twice the first. The sum of the reciprocals of the 2 numbers is 7 over 10. Find the 2 numbers. Now, you should be starting to feel a little bit more confident about these. I would pause the video and see if you can write out what the equation should look like. Just so you know, I am going to call the first number x. Right, so I'm calling the first number x, and the second number is 1 larger than twice the first. So 1 larger means I'm going to add 1. All right, and twice the first, so that's 2x. So my first number is x, my second number is 2x plus 1. And then it says the sum of the reciprocals of the 2 numbers. All right, so the reciprocal of the first number is 1 over x. The reciprocal of the second number is 2x, 1 over 2x plus 1. And I'm talking about the sum of those reciprocals. That equals 7 over 10. Now we need to find the 2 numbers. So again, you could do this algebraically. I mean, just like the problem before, if you do it algebraically, you're going to need to find a common denominator here. I know how everyone loves common denominators. You could do it that way. Or you could put the first part in y1 or y2, it doesn't matter. The second part, y2, all right? And then look at the intersection point. So we're going to do, I think, the easiest way, which is put it in the calculator. All right, so I have it entered in my calculator, and just be really careful about parentheses. When in doubt, just add more parentheses, just better safe than sorry. Now we're going to look at the graph. And we can tell when we're looking at the graph that we have two values here. We have a value here, and we have a value here. We have two intersection points. All right, now, this is important to note. The problem did say that we have two positive numbers, all right? And we know that this intersection point of x, this x value is going to be negative, so we can just eliminate that. We're not even going to check. We know that it has to be this guy over here because this intersection value of x is going to be positive. So we're going to go to second trace, number 5. We're going to move our little spider near that point, and we're going to hit enter 3 times. And we get an intersection value of 2. So we know that our first number is equal to 2. And if our first number is equal to 2, we already know our second number is 2 times x plus 1. So our second number is going to be 5. So we found the two numbers, 2 and 5. All right, moving on to our last page. This is the distance, rate, and time problems. And I'm implementing a table here because I think these problems can get a little tricky. So let's see, a boat travels in a river at a constant speed of 3 miles per hour in still water. It takes the boat twice as long to travel 60 miles upstream against the current than it takes for the 60-mile return trip with the current. What is the speed of the current in the river? So we're going to let C equal the current in the river. The speed of the boat moving upstream is 3 minus C. The speed of the boat moving downstream is 3 plus C. The distance we're traveling either upstream or downstream is 60. And I hope you can see that this table is already helping, at least it's helping me feel a little bit better about these problems. And then we're going to have our time in hours. Now, time is distance divided by the rate. So it's going to be, in this case, 60 divided by 3 minus C, or 60, downstream is 60 divided by 3 plus C. All right, so now we're ready to write our equation. All right, we know that, let's just read this sentence again. It takes the boat twice as long to go upstream than it takes for it to go downstream. All right, so upstream is equal to 2 times downstream. Right, it takes the boat twice as long to go upstream. All right, so 2 times downstream gives us upstream. And now we can just fill in the formulas that we have for upstream and downstream. And our final value is going to be C equals 1 mile per hour. Okay, let's take a look at another problem. We have a speedboat can travel 32 miles per hour in still water. It travels 150 miles upstream against a current, then returns to the starting location. The total time of the trip is 10 hours. What is the speed of the current? Okay, so again, we're looking to find the value of the speed. We're going to let C equal the current of the river, the speed of the boat moving upstream. All right, so this time it's 32 miles per hour plus the current, or it's 32 miles per hour minus the current. All right, so that's going to be our rate. Upstream 32 plus C, downstream 32 minus C. All right, our distance either upstream or downstream is 150 miles. And our time is going to be, time is equal to distance divided by rate. So for this upstream, it's 150 divided by our rate of 32 plus C. For downstream, it's 150 divided by 32 minus C. So now it says it travels 150 miles upstream against a current, then returns to the starting location. The total time of the trip is 10 hours. So let's write this in words. Upstream plus downstream equals 10 hours. Right? When you write it out in words, sometimes that helps it, makes it a little bit easier to fill in the actual math part of the solution. So we know that the upstream equation for time is 150 over 32 plus C, right? We've already calculated the time value for upstream right here. The time value for downstream, which is what we need here because this equation is going to be in terms of time because we're saying the total time is 10 hours. It's going to be 150 over 32 minus C equals 10. And I am not going to do algebra this time because I don't want to find a common denominator from my left side. So I'm going to put this in my calculator and I'm going to look at the intersection point. Okay, I have this entered in my calculator. Right, you can see that I'm using a lot of parentheses because I'm just being very cautious here. I'll take you to the end so you can see this whole equation. Should be 32 minus x. You can use x. All right, we're going to do zoom 6. Let's see if it fits in a standard window. And I can't really see it, so I'm going to just adjust my window. I zoom, and I'm going to go scroll down to 0, or you can just type number 0. I'm going to do zoom fit, and I can see my graph perfectly, and I can see my intersection points. All right, now I know that my value of x cannot be negative. This is a negative x value over here. I mean, I can't have a speed of a negative number. So I'm going to only calculate this intersection. Okay, so I'm going to move my little spider near that intersection point. Make sure it doesn't calculate the one on the left, and hit enter 3 times, and I get a value of 8. Okay, everyone, that's everything for this video. There was quite a bit in this. You're going to do a lot more practice, so don't worry. Thanks for watching to the end. Have a great day.